Behind every great product is a great seal. Join us at the crossroads of preeminent product design engineering, seal mastery, and supply chain excellence, and learn from the makers of our future.
Hello, and welcome to Makers of Our Future. Thanks for spending time with us today to hear from the people behind the products that are changing the world, and for conversations with leaders in the seal industry who are supporting that kind of success. Here at Darcoid, we decided to make this podcast as a store of knowledge, something searchable that you can search up when you're looking to specify your next seal. Let's get started. I'm Bill Sharrett. I'm Senior Vice President of Business Development at Darcoid, and I'm hosting for today. Our guest today, he said, reading from his script, is Craig Rosslee, Dr. Craig Rosslee, actually. Craig graduated from the University of Wisconsin-Madison with a Ph.D. in chemical engineering. Craig's engineering career is rooted in semiconductor manufacturing technologies, spanning from lithography to deep silicon etch. His current role is technical director at Lam Research, where he is team lead for the Syndion GP platform, which is Lam's next generation MEMS etching tool. Craig, welcome to the show.
Yep, thanks for having me.
You bet, you bet. And I should say you're here because Dave Seton recommended you. He was on a few weeks ago and had good things to say about you, so I'm looking forward to the conversation.
Excellent.
So let's start with education. What got you into the game? You started in New York at Buffalo, right?
Yes. So basically, I graduated high school. I had no idea what I wanted to do.
Yeah.
I liked math and science, and so I was like, okay, I could do something, mathish, sciencey. But I also like money. So I was like, well, which of these gets paid the best? Well, engineering gets paid better than being a chemist or a physicist.
Okay.
So I looked at the various engineering, and it was like, well, I like chemistry, chemical engineering. That must be a bunch of chemistry. So I went and started doing that. Turns out it's not actually that much chemistry, but I enjoyed it nonetheless.
Excellent. And then you enjoyed it so much you went into a PhD program. You went west, young man, and to Wisconsin, right?
Yeah. Actually, it was more like I started looking for jobs, and nothing really grabbed my attention. And I was enjoying school, so I was like, let's do a few more years of school. And then the other nice thing about engineering is PhDs tend to be paid for. So getting a PhD, I wasn't incurring any debt. It was I was actually getting a stipend for being a teaching assistant, so it was kind of a free thing to try out.
Okay.
And so I went off and spent 5 years in Wisconsin getting a PhD.
So I know after that you kept going west to Portland, but where is home? Where were you raised?
Well, I'm originally from South Africa. So I was born in Cape Town. And then when I was in high school, my family moved to upstate New York, near Saratoga Springs area. And then, after that, it was off to Buffalo because it was a state college and cheap and easy to afford. And then, Wisconsin.
My English family gives me a bad time for losing my English accent, but you lost your South African pretty significantly. I wouldn't have picked it up. Yeah.
Yeah. Well, when you're in high school and you're the new kid and you're trying to fit in,
right.
It doesn't help to have a strong accent.
Yeah, I hear you. So PhD, armed with a PhD, how did you get involved with Intel? That's a heck of a starting position.
Yeah. So a bunch of people from my research group had started working at Intel, had gone to Intel, when they graduated. And so I was looking at, places to work, and I could work in the oil industry, and that was horrible places like Houston, Texas, or Duncan, Oklahoma. Or then, my, former lab mates had gone out to Intel, and they said, come out and take a look at Portland. And I went out there, and it was amazing and green. And I was like, oh, yeah, this sounds good.
Yeah.
So I went and, started working at Intel.
Fantastic. So you went in as senior process engineer, is that right?
Yeah, well, you start off as a junior process engineer and then managed to get a promotion.
I thought the PhD would get you straight into senior, but no, I guess not.
No, so in Portland, when they do, so Portland's where Intel does its technology development. And so everyone who's brought in there they started a PhD. So they don't hire anyone non-PhD. So, you come in and even with a PhD, you're the new guy who knows nothing.
You're the green PhD. Okay.
Yep.
So what was the learning curve like?
It was rough. So before, when I was actually interviewing for the position at Intel, the guy who was taking me around and showing me, he said specifically at the beginning of the day, he's like, everyone you talk to, ask them about work-life balance. And at the end of the day, he said, look, here's my speech to you. You can have a life and time outside of work with your family and friends, or you can work here. You can't do both. And
That's
so,
rough.
yeah. And so I called up my friends and I'm like, what the hell are you getting me into? And they said, no. Just ignore Fee. Fee's a bastard. You don't listen to him. Turns out he was 100% correct.
Oh, yeah.
But yeah, so I worked there for 5 years and basically they throw you into the fire. And you're trying to, desperately keep your head above water as they throw new stuff at you. And in doing that, you learn just a huge amount. So I'd say, I learned more in my first year at Intel than I did in 5 years of a PhD. So, it's good from that respect. It's bad from, the having a life outside of work respect. And that's eventually why I left.
Yeah. No, I could see how that could grind a person down. Because it sounds like you said you like money, but it sounds like you didn't have any opportunity to spend any.
Yeah.
Yeah. So let's see, you were in the lithography side and were you a tool owner? What was
so I was doing, so I was a tool owner and also doing process development. So in the patterning area, the rule was everyone had to own a tool and everyone had to own some aspect of the process. And then you kind of looked after both. And the idea was that by knowing the tool and the process, you can build a better tool and process at the same time. Because the two, knowing the limitations of the tool is what allows you to know where to turn the process knobs. So that they start. So in terms of development, so you start off with like an older tool and then a quote unquote easier process layer. And then as you prove yourself to be good, they keep on throwing harder and harder stuff at you. So towards the end there, I wound up owning contacts, the contact layer. This is where you connect the interconnect to the transistor. And, the node before that, the person who had owned it had, developed the process and then had promptly quit because they were burnt out. The node before that, the exact same thing had happened. It was just kind of known that you're going to take this, you're going to burn yourself out, and then you're going to do something else.
So you're standing on the shoulders of the person who burnt out before you, pretty much.
Yeah. Yep.
Okay. So it's incremental progress, right? And so far as Intel's your deliverable to Intel is, right? It's okay. Node after node.
Yeah. So I started. It was I think the 90 nanometer node, and then we did 65 nanometer, and then 45 nanometer node, and now they're on like I think like 4 nanometers or 3 nanometers.
So 10, which is 10 times smaller.
Yeah.
Okay, so this is Moore's law, right? And you're in the home of Moore's law. What's that been like? I mean, it's relentless. Going back to memory, there was some talk about photolithography is going to stop when visible light is too big to etch anything meaningful or pattern anything meaningful. What were the big steps there?
Yeah, I mean, it started out. It's you did I-line and then 243 nanometer light, then 193 nanometer light, and then I was doing what was it was going to be the lost 193 nanometer light, and we're going to hit a roadblock. And then they did 193 nanometer immersion, which when they first explained the concept to me, I was like, that's ridiculous. I mean, you've got a layer of water in between the lens and the wafer, and the lens is moving at like meters per second relative to the wafer as it's scanning over it. And it's like, this will never work, but we made it work. And then it's going on to double patterning, where you pattern one layer, and then you offset things just a little bit and pattern do the next pattern. And then eventually it's like, okay, we're going to do EUV, where we're using X-rays and do everything in a vacuum chamber. And that was always going to be 10 years out and was never going to work. And now it's in production. So it's quite amazing.
Yeah. So I can only imagine meters per second. You've got a fluid layer between the light source, if you will, and the target. Is it stepping its way across, like moving, stopping, or is it just constantly moving?
No, it's going back and forth across the wafer. So it goes left to right, and then it hits the end and turns around and goes the other direction.
Mm-hmm.
So it's scanning like S's along the wafer, and then while it's scanning that S, you've got other optical elements that are scanning up and down inside the scanner. Yeah,
I can only imagine what coordination was required to get that to work.
No, the litho scanners are the most impressive piece of equipment I think in existence today. You cannot believe how much engineering goes into them, especially the EUV scanners. It's just amazing what they do.
Extreme ultraviolet, is that right?
Yes.
Okay.
I mean, they say EUV, it's really just X-rays. They're 13 nanometer light. They're doing everything in high vacuum with reflection optics. It's madness. If you explained it to people 10 years ago, they would tell you insane that to believe it would even work, and it's working.
And here we are getting more and more devices per die size. The dies are shrinking.
Yeah.
The wafer is producing many more times chips. I mean, it's all working in concert to support the lifestyle that we're in right now, right?
Yep. And so because of all this magic that we do, you can watch a TikTok video on your phone.
Right. Yeah, let's roll the clock back then, shall we?
Yeah.
So I hear vacuum, and that gets me interested from the seal perspective. Were you switching to vacuum knowledge when you were at Intel, or is that further along in your career?
No, that was further on. So
okay.
So after 4.5 years at Intel, I was completely burnt out. Started looking for other jobs, and then wound up joining Applied Materials. And so they're here in the Bay Area.
Yep.
And at the time, they didn't do anything litho related, and they were starting a joint venture with a Japanese company called Dynippon Screen to try and build litho tools. Not the scanners, but the tracks which cover the wafer and photoresist. And so they recruited me. I went to join them. And then I think 6 months after joining, I went out to Belgium to IMEC, where there's a research consortium where we had placed a tool. And my job was to kind of own the tool, make sure it stayed up and running, and then work with IMEC to generate materials that we could use to market the tool.
So how long was your rotation in Belgium?
I was there for 2 years.
Oh, wow. Okay. Nice. Yep. Getting closer to South Africa and home at that point, right?
Yeah, no, it was actually very nice. One of the big surprises was I went over and was considered a European employee. And they start at 35 days of vacation a year, plus 12 public holidays. So
yes,
the 2 years I was there, the month of February I spent down in South Africa visiting family, because that's summer there.
Yep, beautiful.
So that was very pleasant.
Those European work rules can get very compelling, can't they?
Yes. It was a very big culture shock, because at Intel, you're on the clock 24/7. Like literally, I would get paged almost every night at some point in the night to have to deal with a problem. So when I went to IMEC, I put a big sign on the tool saying, "Here's my number. Call me anytime there's a problem." and I'd come in after a weekend, and someone would have put a sign up saying, "Tool went down on Friday. It'll get fixed on Monday," and it blew my mind.
Yeah, it's a different scale completely.
Yeah.
According to LinkedIn, you were also working TSMC deployment or installation. Is that right?
So yeah, we got the tool up and running at IMEC. We generated a bunch of material that then got companies around the world interested in buying them, and so one of them was TSMC.
Okay.
So they went and said, "Okay, we'll demo one of your tools," and they're like, "Okay, who's going to support it?" And they said, "Well, Craig did a good job in IMEC. Let's send him out there to help with the install." I was actually on vacation in South Africa at the time. I get a call from my boss. He says, "Hey, we're doing this install. Would like you to help out. Can you arrange travel when you get back?" I'm like, "Yeah, I don't have my laptop, but yeah, as soon as I get back, I'll arrange something." He goes, "Oh, don't worry, I'll take care of it." So I get home 9 p.m. Sunday at night, and then 6 a.m. Monday morning, I'm on a plane to Taiwan, and then landed and just if you've ever worked at TSMC, they go nonstop as well. So I landed. I spent 28 days in the lab, 8 a.m. to midnight every day. Got the tool up and running. Came home for a quick break. Went back and did their process startup, and then after that they were happy.
So was that Hsinchu or Taichung or?
Yeah, that was in Hsinchu.
Okay. Yep.
Yeah.
Nice. Yeah, I pre-COVID used to go to Taiwan a lot. We have a distribution center out there supporting our customers. High-speed train going through the technology city. It takes a while for that high-speed train to get past the TSMC facility. It's huge. Yeah, spectacular. Well, I hope you enjoyed the culture and the stinky tofu and the hot pot at least.
Yeah, well, the first 2 trips, is basically work and sleep.
Yeah.
But after that, I got to explore the island. I actually really like Taiwan. You wouldn't know it, but we would always joke that, we're sending you to a tropical island in the Pacific. Oh, it's Taiwan, and you're going to live in a fab. It actually really is a tropical island in the Pacific. They've got really nice beaches. If you go on the east side to Taroko Gorge, it's just spectacular.
Yeah.
But yeah, you've got to get out of the fab to do that.
Absolutely. Well, great deployment. Then you moved on from AMAT to LAM, is that right?
No. So what happened is the joint so the global recession hit, and so the joint venture between AMAT and DNS fell apart, and so I moved back to the Bay Area, and that's when I made the switch over to Etch. So I went from Litho to Etch, and then again, I got to go out to Taiwan to deal with Etch issues in Taiwan, working with a lot of the same people, which was kind of weird. And then that base slowly, I started off learning Etch at that point and started getting into data analytics. So our Etch tools are heavily instrumented. We're collecting lots of data as we're etching the wafers. And so, at one point, my boss was like, "We need to figure out what to do with this data. Here, you figure this out."
Yeah.
So I started figuring it out and got pretty good at it. And then at that point, LAM recruited me to help with a data analytics project they were starting.
Excellent. So by that time, so you're familiar with Etch. You've switched from photolithography, which is less vacuum intensive, if you will. Moved to Etch, which is almost exclusively a vacuum processing environment.
Correct.
Did you have to learn was it difficult translating what you knew, or what is a lithography process and an etch process quite similar or wildly different?
No, wildly different.
Mm-hmm.
Yeah, it's almost like starting from ground zero again.
Mm-hmm.
So I know the basics of what a transistor is. I understand that they care about things like particles and yield. but how the etch chamber works is completely different. And the sorts of things you have to worry about, it really is starting almost from zero again. So it was, I frankly found it very enjoyable. I enjoy learning new stuff. But there was a huge amount of learning that I had to do to get good at it.
Yeah. Yeah. So vacuum process chambers, feed throughs, gate valves, end
Yep.
effectors. That's where I have some knowledge from the elastomer, fluoroelastomer seal side of things. Did you touch on seal technology at all?
At that point in my career, not so much. Um, yeah, that wasn't a part of the tool that I was touching at the time.
Right.
But now, so lately, doing chamber development, that there I get to, touch on this a little bit more. So my current chamber, the Syndion GP chamber, um, you know, we've got all these parts that stack together, and we've got to seal them up, and they've got to, withstand all sorts of corrosive gases and high temperatures, and we really do terrible stuff inside our chamber.
Yeah.
And the fact that they hold up and don't, disintegrate almost immediately is somewhat amazing.
Well, a lot of technical development, right? That's the real leading edge of a lot of seal elastomer polymer technology is the resisting process as long as possible. When it does break down, it's got to break down clean. I mean, we touched on particulate and so on and device size. What are your thresholds for, the chamber needs taking down and cleaning at this point? Because
so that very much depends on exactly what technology you're working on. So TSMC's kind of leading edge process, they're doing, I think, like 3 or 2 nanometer processes right now. 7, 8 years ago now, when I was working with them on like 10 nanometer stuff, they were looking for particles 20 nanometers in size and above. And if you had 1 particle every 2 wafers, at that point, the chamber was no good, and you had to pull it apart and clean it.
Just one per 2 wafer process cycle.
Yeah.
Wow.
Fixing a chamber with that sort of thing, where do you even start?
Because you got to put particles in to remove particles. You've got to clean it, right?
Yep. And so at that point, so it's easy if you get 100 particles on the wafer, because then you can start to look at patterns and say, okay, it looks like it's coming from, this part's rubbing or so on. When you've got 1 particle every other wafer, then it gets incredibly challenging. And so we'll do things like, cycle a wafer 10, 100 times, try and build up patterns, or, take a whole boat of wafers and then run them through and look at all of them and stack it up. They also do compositional analysis for any particles.
Mm-hmm.
So we'll put it in the SEM, look at what it's made of, and then try and identify culprits. And a lot of times it's just, something rubbing in the chamber. And, you look at it, it looks perfect, but just a little bit of rubbing and, there's a 20 nanometer particle on your wafer.
And so it's identifying the source of the particle. I guess that once you've done the analysis, it could still come from any number of components, right?
Yeah. Because a lot of the times you get it as, the particle signatures will show up and it's like silicon, carbon, fluorine. Well, that's half the stuff in the chamber.
Right.
You got your silicon wafer. All your seals are, carbon, fluorine, maybe some silicon as well. Yeah.
Yeah. I remember the transition on the slit valve door, which was the gate that opens and closes to allow that wafer to go in. That used to be an O-ring and a groove, a dovetail groove. And I don't know if you were around or familiar at the time, but that was all rubbing all the time. And it was usually just a simple FKM, not even fully fluorinated. And when the industry transitioned to seal element bonded to that aluminum door, it it dropped particulation by orders of magnitude overnight. It was a tremendous technology at the time. But yeah, that was gross kind of particulation, and then you're getting down to such a fine level. That's got to be a bloody nightmare, Craig.
Yeah. And I mean, a lot of what we've done now is we've transitioned from trying to identify these things and stop them to we'll do things to actually gather all the particles in a chamber and either stick them to walls or flush them down through the vacuum system. So it's more than just let's stop this thing rubbing. It's how do we coat it up so that anything that does rub gets stuck to something. How do we change the way we run the wafer? So I mean, we're running a plasma which will suspend all the particles above the wafer. If you just turn it off, then they drop onto the wafer. So now we do things like a slow ramp down of the plasma, so it gives it time to wash stuff out.
So that's some real leaps in approach there, right?
Yep.
You've got to you've got to be able to think outside the box, right?
Yeah.
So how do you foster that creativity and that being able to say, hey, how about we do it completely the other way around?
Yeah.
How do you get an environment where you can that culture that fosters that?
I mean, it tends to come a lot from the top. So actually, the organization I'm in right now is probably the most creative one I've been in, because the VP who's running the organization is he encourages everyone to throw out your stupid, wild ideas, and you'll throw out your dumb idea, and everyone will be like, "That's dumb," and we'll talk about it and be like, "Okay, maybe it's not so dumb. Okay, let's give it a try." But there's no downside in the organization to suggesting something dumb or trying something and failing, which is very freeing. It allows you to do so much more and try so many stupid ideas that wound up actually working and doing things that we just didn't think were possible.
Oh, that's great. I was thinking of an analog here that I'm enjoying. We build our own test bench facility here, which is kind of unusual for a company of our size, and it allows us. We can fast prototype molded shapes. We can baseline. We can play with them. We can really pull some good data on performance before we take it to the customer level and propose as a solution. So we do a lot of where am I going with this? I think it allows us to be as creative as you can possibly be and really understand the results of that creativity. So I get what you're saying. That's really cool. And I guess you're from the land of Musk, where the best part is no part and the best process is no process. Is some of that creeping into the thought process?
You mean, how do we simplify stuff and make it easier?
Yeah.
I mean, we're constantly trying to make things simpler. The problem is that our goalposts are constantly moving as well.
Right.
So, I figure out a way to do something simpler today, but the customer doesn't want that. He wants what he wants tomorrow. So inevitably, our tools are getting more and more complicated, and we're adding more and more knobs to the tool and more things to break down. And so, I mean, as engineers, we all want it as simple as possible. But to deliver what we need to, we just keep on adding complexity on top of complexity, which is a challenge. It's a real challenge to manage.
Yeah. So your product, the MEMS, right? The end user's looking for more capability, more functionality from a smaller piece of silicon, right? So I can only, and those are moving parts, yeah?
Yes. Yeah, the MEMS is, if you talk to the guys who are making like your logic chips, they'll say, okay, MEMS is easier because it's all bigger stuff. But having done both, I can tell you it's not any easier. It's just different challenges. So in the MEMS space, we're not as worried about particles because our features are bigger. But I've got customers telling me they want to etch away for 20 microns a minute. The logic guys are actually etching at 20 angstroms a minute. those are
Wow.
very different challenges.
Yeah. Wow. So you've developed a tremendous amount of experience. You've built on knowledge that and experience that you've picked up along the way. How does someone starting out in the field, how does someone look at you where you're at now and not go, oh, how could I ever accumulate that kind of knowledge and experience? What would you say to someone who's considering this as a career path?
I mean, I would say that the key thing, if you want to get all this experience, is you need to spend the early part of your career always in an uncomfortable, like you're almost over your head sort of feeling. So if what you're doing is feeling easy and you kind of know what you're doing, then it's time to move on and pick tougher challenges, or pick a different company that's going to give you tougher challenges.
Mm.
Um, you know, Learning all this stuff, it's exciting, but it can also be a little unpleasant when you're handed something and you're told to make it work, and you look at it and go, "Oh my God, I have no idea what to do."
Yes. Yeah.
Um, and yeah, struggling like that is the absolute best way to learn stuff.
No, that's a good perspective. So it's like, if you're not feeling pressure, you're not developing, right?
Yeah.
Hmm. Very good. Do you deal with interns? Do you work with interns? Because that's obviously a great way for you to look at potential
Yep.
employees and vice versa.
Um, yeah, I've had some interns come and go. The other thing we have is our company is a new hire rotation program, where they take recruit a bunch of what they consider high potential graduates, and then give them 6 month blocks in different areas, to go ahead and try these different areas and figure out what they want to do. I work a lot with those people and the interns. I must say that they've all been amazing. Um, I'm amazed at their work ethic and what they come in knowing. Um, and I throw them challenges. I try to keep things difficult, but not too difficult for them.
Yeah.
Um, and uh, you know, the feedback I've always gotten from them is, "This is great. Can I come and work with you full time afterwards?" Um, so I think I'm doing something right there.
No, nice. And talking to Dave Seton, he did say it was a surprisingly competitive environment to be picked up as an intern at Lamb.
Yep.
So you're clearly a pinnacle that people are recognizing and valuing and wanting to be a part of.
Yeah.
Excellent. Do you have any involvement, or what would you say when, I know we're talking before the show, you mentioned the only time you know about seals is when they're not working.
Yep.
Who do you go to when there is a problem with or a challenge with a seal?
I mean, the first place I'd go to is my mechanical engineering team. So, on our team, we have people whose job it is to know about seals, and to be able to suggest which one is the right one to go,
Yeah.
to use for a specific um, you know problem. And then those guys, I mean, they're working on lots of other things. So this is a small. They have some knowledge, but not a ton. So if we're
Yeah.
really going to extend and try and do something beyond what they know, at that point we'll pull in the manufacturer of the seal and talk with them, and kind of work our way up the food chain,
Yep.
to find the guy who knows what can help us with our problem.
Great. And are you ever wheeled into those conversations as the Ph.D. in chemistry that can talk turkey at that level?
Thankfully, no. Yeah. So, I'm a chemical engineer, not a chemist. So,
Right.
it's surprising how little chemistry I actually know.
Okay.
I mean, I can just set up a distillation column, but in terms of figuring out how to create something, which products to use and so on. Yeah.
It is a very specialized field, that's for sure.
Yeah.
People just say, "Oh, put an O-ring in there," and what kind? Well, a rubber one. It's like, no,
Yep.
it's yeah. That's there's a lot of technology and specialty in well, any of these components that are major components of chambers, right?
Yeah, no, nothing we do is simple.
Mm.
Every single thing we do, there's it's reached the point where everything has to you have to get the details right on everything.
Yeah.
Even anodization on an aluminum part, that used to be dead simple.
Right.
Well, now we've got all these detailed specs about, you've got to do it this way, it's got to meet these criteria, because we've learned these things the hard way that, you can't just dunk it in a bath and go, okay, it looks black, it's good enough.
Yeah, because you're constantly chasing particulate, and you need to
Yeah.
lock it down, right? Yeah.
And the chemistries we work with are just horrendous. I mean, for silicon etch, we're using fluorine-based chemistries. I mean, you could put sand in the chamber and it'll eat the sand.
Mm.
So, yeah, if you don't have the right stuff, it's not going to survive.
Very unforgiving. Yes.
Yep.
So, thinking on your career, what stands out as something you're real proud of, your biggest achievement, whether it's technical or milestones, as you reflect on where you've been?
Yep. I mean, I would say the stuff I've been doing recently, I'm doing chamber development, leading a team that does chamber development has been incredibly satisfying.
Mm.
Taking something from where, the marketing guys come to us and say, hey, I want a chamber that's going to do X, Y, Z. And you go, but that's impossible.
Right.
To sitting with the team, figuring it out, throwing these wild ideas against the wall. And then, 2 years later, you deliver this thing and they go, oh, wow, this is meeting everything I want. And then the customers are buying it. I mean, that's my baby out there in the world and people are praising it. So
fantastic.
I'd say that's, yeah.
And a whole new chamber platform, that's a biggie. I mean,
yeah,
there's so much that goes into that.
Yeah. And to be clear, it's not completely new ground up. Everything we do is we're starting with, the previous iteration of it and we're adding stuff to it. So, in the current chamber, probably only 25% of it is brand new. But still, I mean, this thing is incredibly complicated, and 25% is, it's a team of, 15 people working for a year and a half full bore.
Yeah. No, fantastic.
Yep.
Shout out to Lam. As an organization, as a culture, why would an engineer be crazy not to consider joining Lam? What is it about Lam that's great?
I mean, the culture is definitely a big plus at Lam. It's, they're a very data-driven organization. It's much more data-driven than some of the other places I've worked at. And it's tough, challenging problems. It's not boring. The absolute worst thing for me is sitting around bored. I can't deal with it. I always find something to do. And working at Lam, our customers are always giving us tougher problems and we're always trying to solve them. And you never know, what the solution is, or even if there is a solution. So you're going in there and you're trying new stuff every day. So, that's just incredibly satisfying and enjoyable.
Excellent. Good. Before my last question, how should someone contact you, or if are you open to contact to learn more about Lam, or directions to a website? How do you want to play that, Craig?
I mean, I'm not a people manager at all. I'm a technical guy. So if you're looking to get hired, I'm the wrong person to talk to.
Yeah.
Because I'm going to say, hey, I'm not hiring anyone. I would actually point them to Dave Seton because he's my manager and he's the one doing the hiring.
Okay.
But if they're interested in talking to me about what's it like at Lam, I've got my LinkedIn profile. Craig Rosslee, just search LinkedIn, Craig Rosslee, Lam Research, and you'll find it.
Excellent.
And I'm happy to answer questions there. But I'm just going to tell you should apply to Lam and give it a shot.
Sure, absolutely. I wanted to throw that out there for you. All right,
Yeah.
here's the last question. In technology, in life, we stand on the shoulders of giants, right? The people that have come before us. As you reflect, who gave you the best advice that's gotten you where you are today? And what is it? What would be a good old nugget to pass on to those coming up right now?
I mean, I think it would maybe be my dad, who told me, the behavior you accept is the behavior you're going to get. So if you put up with, people not meeting on commitments, you're training them that they don't need to meet their commitments. If you put up with someone who's, being unpleasant to you, you're training them that they can do that and get away with it. So, kind of, stand up for yourself, call out bad behavior, call out good behavior, and you'll find yourself in a better working environment.
Rules to live by. You can't go wrong with that. That's great. Is there anything that we missed in this conversation that you'd like to touch on, Craig? I really enjoyed the ground that we've covered.
Yeah. No, I mean, I think I just want to stress again, as a young engineer, you should be pushing yourself and trying new things and, live in that slightly uncomfortable zone, because in the end, it pays off pretty nicely. And, you're going to learn a lot by doing that.
Fantastic. Well, on that note, I think we'll wrap it. Craig, thank you so much for your conversation today. We'd never met before the podcast. I was a little nervous about that. I really enjoyed getting to know you. It's been a pleasure.
Yeah. And thanks for inviting me on the podcast. It's been fun.
Sure. Thank you. And to our viewer and listener, thank you for listening. And we'll see you next time. Thank you very much.
Thanks for listening to the Makers of Our Future podcast. Behind every great product is a great seal. Learn more about how we can help at www.darcoid.com. That's DARCOID.com. The best seal, on time, zero defects, Darcoid.